Okay, so we left off talking about the one-dimensional nature of MAC addresses. A MAC address just says this is a particular device on the network. MAC addresses are crucially important for switching, layer 2 technologies, and to understand how they're used in switching, I want to just go back through the basics of how all this stuff works at layer 1 and 2. So, very quick kind of history lesson here in a way. In olden days, and I do go back that far, we had the original Ethernet. So the original Ethernet was actually one big long cable. It could be 500 meters long. And individual computers were attached to it. This is where the term shared segment comes in. All the computers, so maybe this is 1, 2, 3, 4, these are all PCs. All of these devices, these computers, were physically attached to one cable. And what that meant was they couldn't all talk at the same time. Because if two devices try to transmit onto a single cable, they're going to interfere with each other and you're going to get garbage. Yep. So this idea of a shared segment gave rise to the media access control methods that we use in Ethernet. Incidentally, this is why in network diagrams, when you see them talking about a LAN segment or something like that, it's usually drawn like this as just one line. It's for historical reasons. Physically, they don't look like that. It's individual computers plugged into switches, but this is how it started. So if you had a shared segment, there were some problems that would crop up. So you had contention, you had collisions, and you had broadcast radiation. So contention, what did that mean? That basically meant that the more computers you added to this segment, the lower the amount of bandwidth overall everyone gets. So if you had a 10 megabit Ethernet segment here and you have one computer on it, it's got the whole bandwidth to itself. If you have two, then minus overhead, they've got about 5 megabits each over time. If you have 10, they've got 1. If you've got 100, they've got 100K. It starts to go down very rapidly. So the more computers you have, the less share of the network bandwidth everyone gets. That's contention ratio. Although in reality, only one machine can talk at a time. So what that means is when one is talking, when one computer sends information out onto the network segment, then nobody else can talk until this one's done. Yeah. So that's the basis of what a contention ratio is. Then we had another issue, which was collisions. And that meant if you had a malfunctioning network card, or you had a cable segment that was incorrectly specified, it was too long, you could have the potential for machines at one end and machines at the other end to have a high enough latency between them that they didn't realize someone else was on the network and they tried to transmit at the same exact moment, and you get a collision, interference, data garbage, you know. So this was another issue with original shared segments. Then we had an issue called broadcast radiation. What's that? So now we bring in different types of network traffic. So frames can be, or packets can be unicast, which means they're going from a particular source to a particular destination, a known destination address. They can be multicast, which is from one to a group of destinations, or they can be broadcast, which is from one source to everybody. I'm going to say everybody on a segment. So why do this kind of broadcast thing if MAC addresses tell us who everyone is? There are some network services which in the early days evolved to take advantage of the fact that everyone was connected to the same segment. So say you had a network file server attached to a shared segment. It could announce its presence by either sending individual packets to every single user on that segment, maybe 100 users, 100 packets, every so often to say, I'm still alive, you can still use me. Or it could send out a broadcast, and the rules of broadcast traffic mean everyone has to stop what they're doing, CPU interrupt, open up this packet, look inside and see if it's for them or not, if they have to do something else. So using that kind of broadcast rule that everyone has to open it, it seemed pretty efficient for people designing network operating systems like Microsoft and Novell. They could just say, network resources, we'll announce them through broadcast. Much more efficient. But then they started doing that for everything. And also, individual machines use broadcasts as well. So, you know, later on we'll get to address resolution protocol. That starts out as broadcasts. So it's this idea of everything has to open it. But we get to a point where if you have too many computers, devices, and they're all generating broadcasts, then the network performance goes way down because everyone has to stop what they're doing every time there's a broadcast and process that first. So pretty soon machines stop doing actual work and start processing broadcasts more. So we had these three problems. So how did we kind of solve some of these things? Network topologies started to change. So instead of this, initially we got hubs, which was we could have our same 4 computers. But now they're physically attached to one device called a hub. The hub is just repeating the signals. So in effect, it's behaving just like the cables did before. Everyone still shares bandwidth. The more computers you have attached to this hub, the less bandwidth everyone gets, etc. So why bother doing it if you still have all these problems? Because physically, you solve things like somebody cuts through the cable accidentally. You know, somebody cuts through one of these cables, one computer is affected, not 24 or hundreds. So hubs helped us with the physical topology and reliability there. But they're basically acting the same way as the original segment did. So they still have contention, collisions, broadcast radiation. So we're not doing too well. So what did they do next? They said, well, maybe an approach here is we could reduce the contention ratio by splitting the network up. They call that segmentation. So they said, let's say we've got 8 here. Instead of having all 8 computers attached to one segment, let's have some kind of device in the middle, which we'll call a bridge. This is the network symbol for a bridge. which splits one big network segment up into two smaller ones. 5, 6, 7, 8. And the idea there is that traffic which is unicast ends up staying on the side of the bridge that it needs to stay on. So for example, if 1 wanted to send information to 2, then the bridge would keep that local. If 1 wanted to send information to 5, the bridge would pass the frame across. Yeah. So as things scale up, if there's a lot of traffic between machines over here, then you get a performance benefit by keeping that on this side of the bridge. Same over there. But some traffic will have to cross, you know. But it's not perfect. It helps reduce contention ratios, but we still have issues here. So essentially we have a shared segment over here and a shared segment over here. So the bridge works by running something called the transparent bridging algorithm. It's transparent because the computers don't know it's happening. That's where transparent bridging comes in. And the way it works is it keeps a list of every MAC address it sees. It keeps a table called the bridging table. Bridging table. Now let's imagine that every one of these computers is going to have its own MAC address. And instead of writing out all the hexadecimal every time, I'm just going to say that the MAC address of 1 is going to be MAC 1. Really, it would be a big hexadecimal thing. Okay? MAC 2, MAC 3, MAC 4, MAC 5, MAC 6, MAC 7. If I put an H on the end of this, it could get to Australia in like 4 hours. MAC 8. Okay, so they all have individual MAC addresses. The bridge has to follow 3 rules. It has 3 tasks. The first is it can forward a frame if it knows the destination MAC address it's going to. So I can forward if I have a known unicast MAC address, known unicast packet. If I don't know, I have to flood the traffic. And I do that if I have an unknown unicast packet. It has the MAC address of an individual machine, but I don't know where that is. Or if I have a broadcast, because broadcasts have to go everywhere, or a multicast. Because I don't know where these things are. Okay? They don't relate to a specific machine. I can also filter frames if I know I don't need to send them out of a particular port. Okay? So these 3 rules, forward, flood, filter, are the rules that the bridge follows, and they're also the rules that switches follow when we get into that. So machine number 1 with the address MAC 1 wants to talk to machine number 2. So machine number 1 sends out a frame onto the local network segment, the shared segment. Initially, machine number 1 might not know the MAC address of machine number 2. So it sends out a frame which has a source MAC address of MAC 1 and a destination MAC address which is all Fs. And all Fs means broadcast. 48 bits of 1s broadcast address. So this, initially, we don't know where 2 is. So we send out a broadcast to say, an ARP really, to say, what is the MAC address of machine number 2? So I can send something directly. This now, because it's a broadcast, gets sent to and opened up by every single device attached to that segment. So all the other computers get it, so does the bridge. So the bridge learns by opening up this frame that, or looking at the header, that machine number 1, which has the address MAC 1, is located out on port gigabit 01. To get a bit more real about stuff. So GI01 has this MAC address attached to it. Everyone gets this. 3 and 4 just throw it away. MAC 2 replies to the ARP to say, oh, that's me. So everyone gets the reply, including the bridge. So the bridge now knows that MAC 2 is attached to port 1 at this point. However, when we sent out this broadcast, the bridge didn't know where MAC 2 was either. It didn't know where computer number 2 was. So what are the rules there? If I don't know, I have a broadcast. If I don't know where the destination is, because it's a broadcast, I have to flood the frame across to all the other ports. In this case, it's only 2. So that means everyone over here gets this broadcast as well, whether they wanted it or not. Now, this is why it isn't, bridging, switching isn't perfect. It does nothing to stop broadcasts. So this very first frame was broadcast, everyone got it. The bridge didn't help us out performance-wise. It just behaved like a shared segment. But when machine number 2 replied to machine number 1, the destination address of that frame was MAC 1. So the source address is MAC 2, the destination address is MAC 1. So now, when everyone gets this frame, because it's a shared segment with a hub, when the bridge sees that reply, it learns, first of all, where MAC 2 is, and also the destination is MAC 1, and it already knows that MAC 1 is on this side. So the reply can be filtered, and the reply doesn't need to be sent to everyone over here. So over time this builds up, and the switch learns that MAC 3 and MAC 4, all these computers are located on port 1, and all these computers all these computers are located off of port 2. So the bridge learns where MAC addresses are and stores that information in the bridging table. So all of these MAC addresses are associated with specific ports. And because it knows that, any traffic that would be contained inside one segment can stay there. It doesn't have to go across to the other side, which gives you a performance benefit because a lot of that unnecessary traffic is being kept off parts of the network that it doesn't need to be on. Yeah. Okay. So if we have known unicast traffic, the top one here, then frames can be forwarded out of the ports that they need to be and filtered off of the ports where the destination is known not to be. But if we have broadcast frames, like ARPs, for example, they're going to go across anyway. If we have multicast frames, they're going to go across too. So switches do nothing to help us with excessive broadcast traffic. Okay? But they do help us with contention, because we've reduced the size of each segment. Okay? So I'm talking about bridging here, but really a bridge is just the first generation of switch. So if I add on more segments, then we have a switch. So say we've got gig 03 or something. So switches are G-port bridges, you know. And commonly now we have switches with 24 ports or 48 ports down at the workgroup level. Big core switches can have like 384 ports, for example. So switches run the exact same algorithm and treat the traffic the same way. Multicast, unicast, unknown traffic, known traffic, all that stuff. The rules still apply when we're talking about switching. And they build a bridging table, it's just that there's more ports on it. So the next evolution of that was something called switching to the desktop when it first came in. And the idea there was, instead of having computers attached to hubs, which were then attached to a big expensive switch in the middle, you got rid of the hubs completely. And each computer is attached to its own dedicated switch port. By doing that, we solved the second problem, which was collisions. So now there can be no collisions on the segment if it's not shared with anyone. So if we have one computer attached to its own network segment, then you don't have any collisions. So each device gets its own port on the switch, which is normal networking now. Okay? Has been for a long time. So now we don't have collisions, we don't really have contention. In effect, we've kind of brought contention into the available bandwidth of the switch and its uplink towards the core of the network. But we've certainly reduced contention issues a lot, but what we haven't done is solve broadcasts. So just like before, if computer number 1 sends a broadcast out onto the network, everyone still gets it, even though they all have their own switch port. So switches don't stop broadcasts. If you want to solve that, you need a router, okay? Because routers define boundaries between broadcast segments. So this slide here is pretty much showing what I talked about in that example. We have a switch with 3 computers attached to it. So we have machine number 1 attached to port 1, machine number 2 attached to port 2, 3 attached to port 3. They all have their individual MAC addresses, and these are stored in the bridging table of the switch, which in Cisco is called the CAM table. Okay. So the switch knows which port is associated with which computer by the MAC address. That's how we know where everything is. So we can filter traffic off of ports that it doesn't need to be on. And the way the switch builds the MAC address table is by listening to the source MAC addresses of frames as they go through. Okay. And this is just showing the process, pretty much what I was talking about there. This is a crucial thing to understand, because the process here and the bridging table itself is the core of how a switch works. It's also key to a whole load of other things that are done in campus networking. So you'll see a column there for which VLAN a particular port is attached to. There's also a lot of the security mechanisms and attacks, actually, that can be employed against switched networks are exploiting weaknesses in this or using this. So, for example, you have attacks like MAC spoofing, which try to do a man-in-the-middle attack by using bad information that's put into bridging tables. We also have CAM overflow, where you try and max out the amount of memory to hold the bridging table. If you manage to do that, it turns the switch basically into a hub again. Can't learn new MAC addresses. And we also have security built onto this. So if we have static MAC addresses, we can say only a particular computer is allowed to be attached to a particular port. So somebody can't plug in their evil laptop and wreak havoc on our network, because the switch is just going to go, I don't recognize that MAC address, go away, you know, shut the port down, it'll scream for help, you know. And we can also use the idea of trusted ports. So if we know that a DHCP server should be located off a particular port, then, and we know that because it's in our MAC address table, we can actually say if we get DHCP replies from other ports, something's wrong here. It's malicious, you know. So the bridging table is core to how the whole thing works. If we can't put entries in our bridging table, the switch doesn't really function. Yep. Okay. And it's all based on MAC addresses. But these MAC addresses, like I say, only say, I am machine number 1, I am machine number 2. You don't say where I live. Okay. On the switches, you can see this MAC address table easy enough by saying show MAC address table. You can also limit what you see to dynamic entries learned by ARP as machines discover each other and the switch listens to it. We can see statically entered entries. So if you have a very security conscious network, you might want to hard code MAC addresses or specific ones. So we can see these as well. And you can see which MAC addresses are available through a specific port if you want. If you are only seeing one, it's probably an access port with a computer attached to it. If you're seeing hundreds, then you've probably got a trunk link there. You know? We can also see these by VLANs, but we're getting into VLANs after the next break, so I'll talk about that then. So MAC address table, CAM table is crucial. Okay, starting that later. So, briefly, I just want to talk about what we're covering in Layer 2 technologies before we have another break. So, what we're doing in this module in terms of syllabus is the same as the CCI lab exam syllabus. So we're covering VLANs next. We're covering different port types. We're covering VTP and trunking. VTP requires trunking to work. And we're going to be looking in quite a lot of depth at the different flavors of spanning tree. Then we'll look at link aggregation, Ether channel in Cisco, lag groups to everybody else. And then some other things that we'll encounter along the way, like mechanisms where we can improve the reliability of our network, like UDLD, unidirectional link detection, and further on we'll talk about span and extended span and all this kind of stuff too. The focus really is on our core bridging topics. So we're really talking about VLANs, trunking, Ether channel, spanning tree especially, and VTP. Okay. So these are things you'll have seen before if you've done CCNP, but especially with spanning tree, it's vital to understand that if you're going to be able to troubleshoot Layer 2. Okay, so we'll take another break.